So, yeah, welcome everybody. So we do lecture 8. That is the lecture where we actually don't have a lecture. We're going to talk about projects, and we're going to talk about the different ways you can use measurement tools, and what these measurements actually entail and what you get out of them. And they're all based sort of on the fundamentals that I taught you in the first 7 lectures. And but I wanted to see you what happens when you actually use these measurements in practice. Okay. So this today is demo day. Yay. And we have a bunch of other things too. Oh, I forgot. Yes, we have statistical versus non-statistical machine learning. I wanted to show you something with that, but I actually forgot that in the car, so I'm going to do it next time. And then we're going to do more on the TF meter because there were questions in the Piazza, and I was wondering, I was going to answer them. Then I show you the measurement tools, and there are 2 main tools you can use. One is Brainome, which is, again, a company that I'm the CTO of, and that will basically give you free accounts, and you can just use them and use that for your project. Or if you want to see more open source stuff, this is stuff that has been developed by students, including the TF meter and so on, that you can derive your own measurements from. And both of these are okay. Obviously, the open source stuff doesn't have as much depth, right? So for example, the open source stuff only assumes balanced binary classes, while sort of in the Brainome tool, you actually have everything, right? Multi-class, imbalanced, all of this is taken care of for you. Obviously, yeah, a commercial solution has to deal with everything. And then we're going to spend hopefully some time on projects, especially for people we're still looking for people. I got a couple submissions, which I'm going to go through over the weekend, and I'm going to give you feedback. But I don't think everybody submitted, so we will see what's going on. Okay, so let's talk about. So first of all, any questions? Because today is totally open session. I have no more slides. Okay. Any questions about the lecture so far? Any questions about the project? Any questions about anything, in fact? Okay, there are no questions, which is totally fine. Then let's start with TF meter. So TF meter, right? So we go here, tfmeter.xv.berkeley.edu.
Professor?
Yes.
I think that someone had a question in the chat.
Oh, thank you for showing that to me. I have a question. So Mesut has one, and then also, I don't know. Okay, Eleanor's off topic. That's okay. And the answer is, darn it, yes, I need to send you a form. And then Mesut, what's your question? Mesut?
Oh, hi. Sorry, I realized I was not muted. Yeah, I do have a question. So I guess, what's the? I know I saw like the paper, like the project report from Rishi, but I'm just wondering, do we want to reach a conclusion with our project? Like, do we have to reach a conclusion based on from our project, or like, is it enough for us to just investigate, the effect of something? Like, is that, I don't know if that question makes sense. Like, do we have to have a concrete conclusion about the things that we want to investigate?
No, it is, I want you basically to comment or use the experimental design principles that you learned in class. It's basically more like, look, you listened to me for how many lectures?
I see.
Right? And for me, it's important that you start measuring along design principles, right?
Right.
Yeah. Okay. And then there were questions. I don't know who asked them on Piazza. I would have to double check. But there were a couple of questions about memory equivalent capacity and TF meter. And one of the question was, wait a minute, why does this show 4 bits here, right? So right now we have 1 neuron. This should be 1, 2, 3. Why isn't this 4, right? And the answer is there's actually a hidden layer neuron in here. Sorry, an output layer neuron in here. So if I actually make the 0 layers, then you get 3 bits, right? So the single perceptron is behind the picture, okay? And that's a little bit of a design flaw in terms of the GUI design, I think. But it wasn't from us, and we took this from the actual flow playground. And so that's where that came from, okay? So let me know, like, if that answers the question. I wonder who raised the question, but it was also public on Piazza. So that is the first thing. So obviously with 3-bit, by the way, you can totally do that separation here in 2 dimensions. Bam. Okay. Now with 3-bit, you cannot do this. There's like no chance in hell. Right. And so this is how this looks like. But basically those 3 bits are just basically your one line in 2 dimensions, right? And then you could add, you know, a hidden layer, and then obviously you have 1, 2, 3 plus 1, 2, 3 is 6 bits, plus the 2 output bits that I mean, there is the output neuron, which is 3 bits as well, but then it's limited by the output here, which is only 2 bits, so it's 6 plus 2 is 8. Okay, and with 8 bits, you can start thinking about the separation, but really not yet. It's better to, it's better to like add another bit, add another one, and then it just works really easy. Yeah, if you don't make that sigmoid by ReLU, guess what? That's even better. Done, right? So yeah, so that's basically the idea here, and there is this hidden output neuron that obviously adds to the total memory equivalent capacity of the network. Yeah, any other question about that? Okay, so I want to show a little more what you can do with this tool. This is actually kind of nice. So the major trick here is you see 2 numbers, of which the second number is really not that important. This expected number is basically building a stupid network, as we call it in lecture, and then taking the log of the number of connections that were needed there, and saying that the expected capacity demand would be 12 bits. But also it's important, that's all for memorization, okay? The trick is that the funny thing is that the original TensorFlow playground blurs those lines of generalization and memorization, because while there is test data, the test data clearly is so close to the training data that it's, you know, that yes, pure memorization wouldn't do it, but actual memorization, but I mean, basically, it's really nicely chosen test data, right? So that's why this works, right? So there could be other test data and so on, and then this wouldn't come out so nicely. But it's an academic tool, right? And so same here, like this is literally, if you have a perfect training split, you're fine. Same here, right? I mean, these points are literally sort of on the same spiral, right? And when you talk about these structures, for me, this is not a distribution, right? They're not distributions. They're just basically structures and defined rules between the structure, right? And so, for example, that here obviously is nothing else but XOR. And we have to start from scratch. Yeah, it's interesting. So the XOR wants 12 bit, 11 we don't get it, so let's do 14. But even then you can have trouble. Yeah, that's a lot better. Here we go. Right. So the trick is, the trick again is that this works so well because we can actually call it expected versus just upper bound for overfitting, because memorization and generalization is very close to together. Now, the thing immediately changes if you kill the signal strand, right? So if you go ahead, let's call it this one, and make the signal strands like crappy, right? Then you will see that you have to get really close to actually memorize on each individual point, right? There's nothing you can do at this. Like, this is just random points at this point, right? So, yeah. And so a little bit the problem is that this doesn't seem to update right. So this is there's a bug here that I just wanted to notify you guys. Because reality is that here cannot be 14 bits, right? There's just no way in how. Right, but we get to some. I mean, if you think about it, the training and test loss, right? So we have we get to a little bit higher than than best guess accuracy by doing that. Right? Okay, so more in the chat. Might be a trivial question: how to integrate the test train loss in percent? Why it's sometimes over 100%? It should. Oh, you okay? No, so you don't add the numbers. So you could have 100% test loss and 100% train loss. That it will be 200%, but that's not the point. It's percentages. You don't add them. The max is 100%, and it just means that they're measured independently. Train loss means you have a train loss. That basically means how much, what is the error in your training, and then test loss is what's the error in your validation. I think that should answer the question, right? Yeah. Then the generalization, you have to be careful, right? So the nice thing, you could have huge generalization. For example, let's make this really huge, right? Now we have like 100 bits per bit generalization, right? So just doing one linear cut. But obviously that's cool. Yeah, all the 100 points are now basically, memorized or basically generalized to one line. But that's the problem, right? What you get there is nothing else but almost like the average or something, right? What you get is very high test loss, very high train loss, which in this case actually is above the best guess, right? The best guess would be 50%. That's all you can do, right? So generalization by itself is not it. It needs to be the trade-off between generalization and memorization, right? So you can see that here very, very clearly. The other thing that I usually point out to people, and let's choose a less noisy image. For example, let's use this one, is when you add a lot of layers, right? So this tool allows you to add a lot of layers. Okay. Oh my God, this is so much work. Yeah, you see there's no training. Nothing happens there, okay? And this was formally called in the 90s, I think, the vanishing gradients, right? And does anybody know of you how I would describe this vanishing gradients phenomenon, right? So first of all, let's do this. Let's take the learning rate really low. We take it to really keep all of this, and then we just go, okay? Why on earth don't we see any activity in this neural network? Can you answer this question? Any idea? Let me pick random people. Mesut, any idea? You can also just say no idea, that's fine.
Sorry, I'm not very sure.
It's okay. Why on earth can't we train so many layers? There's 10 hidden layers. What happens? So what happens is this. Let me explain. Remember when we went this way, like from the left to the right, right? We said there's something called the data processing inequality, right? That means data cannot be created from one layer to the other. That means the first layer here has some capacity, and then you go from to the right, to the right, to the right, to the right, to the right. And it turns out, for example, and we can see this here, that if I delete, nothing happens to the memory equivalent capacity. You guys see that? Even though I delete those neurons, nothing happens to the memory equivalent capacity because they're already so dependent on the other ones that it doesn't matter to have them. They're completely redundant, okay? Now comes the interesting question. What happens when we do backpropagation? When we do backpropagation, we have the same problem. So while there's a gradient of error on the very right, where it's called output, right? That gradient of error goes to the left and backpropagates. And that means, of course, that there's a dependency, a dependency, a dependency, a dependency. We do all these chain rule, derivatives, right? And of course, that also obeys the data processing inequality. And what that means in the end is that you lose information from the right to the left, just like you lose it from the left to the right, right? So nothing happens here in this case. The only way to train this network really is to get rid of all these extra layers. And you get something like 3 layers, you see the things happening again slowly. Well, this is maybe too slow, but right, you see, here's something good happening, right? And you also see a lot of redundancy still, right? So I can totally get rid of all of this here. Nothing changes. Okay, that changes something. So if I do the same thing again, ta-da, right? So the trick is that the data processing inequality exists in any graph. Okay, you go from left to right, you lose information because you want to. In the neural networks, you want to lose information. But if you go from right to left, where you train the network, you have the same problem. And you have 10 layers. Yeah, it's called the vanishing gradients problem. You just basically there's no information left to update these first layers. And on top of the point is that these updates here need to be a lot stronger than those updates, because the updates here are really fundamental ones, like these lines. And then these are just combinations of those lines, and they can correct a bunch of errors. But if the update in the first hidden layer isn't right, because there's nothing that can be done, that's why you can't train neural networks that have too many deep layers. Okay, it's again the data processing inequality. So that is something that is really, really useful in this app, and to just play around and try. Also, my students in my multimedia group have started adding sort of stuff that you can actually put your own data set in, and all you have to do is basically create a comma separate value file that has x1, x2, and a target, which should be binary, and then you can automatically get this expected capacity demand, and you can also automatically play around with it, try to train it, and so on. Okay, so that's something I would also, if you want to play around with this and get sort of an idea for the measurements and how they sort of are rooted in this, please do so. It will make your understanding a lot better. Okay, so any other question about TF meter and this app?
Professor, I had a question.
Yes.
So you talked about vanishing gradients, like problems being caused by like too many layers. Mm-hmm. But I thought part of the problem have been mitigated by the residual connections. So could you is there like functionalities in TF parameters that account for residual connections, or like is that something that we normally don't consider?
Yeah, so there is a version of TF meter that actually has residual connection. I think it was called beta or alpha or development. Okay, I will find it for you. And yes, the vanishing gradients. Oh, I don't know what this is. Cancel. Cancel it. The vanishing gradients problem can be solved with shortcuts, right? Remember, the shortcut network is the ResNet. And of course, that makes total sense because now you could have a connection from the first hidden layer to the last hidden layer. And of course, then this update then doesn't lose that much data because it isn't filtered by all these neurons in that. So that's completely right. That would help. But now you have this problem that what if you had a fully connected network, right? So something where instead of this typical bipartite, tripartite graph that you have, you would actually connect everything to everything. Well, the problem then is you have a combinatorial problem. You have so many weights to update that training takes forever, right?
Yeah, and I guess, yeah, I agree that it will take, it'll create a lot more parameters than probably necessary. And, it also makes the training hard, which also makes the training harder. But I guess on this topic, like, how do we, is it possible, like, how do we calculate the network capacity for neural network with residual connections? Is there a way for us to do that, or if not, like, what's the reason, or like, what are the closest thing we have?
Yes, good question. It's the same thing. What you do is you just have to skip rule 4, right? So rule 4 says the capacity of a given layer is limited by the output capacity of a previous layer, right? Well, you can calculate the capacity of that layer and you have ResNet connections going in, you just count the number of ResNet connections. And it's still true that the capacity is limited, but usually it's not, because if, for example, the connection comes from the very beginning, then you need to assume that you have all the information at hand. So
yeah, but sorry, go ahead.
No, the 4 rules just apply. You just have to think about it.
Yeah, but if, let's say we have 3 layers. I mean, I'm just making these numbers up, but we have residual connections from both layer 1 and layer 2 into the 3rd layer. But I feel like the information gain from the residual connection coming from layer, okay, sorry, I should say when, okay, anyway, let's say we have 100 layers, and like the 100th layer have connections from layer 1 and layer 2. And but doesn't some part of the information we gain from the residual connection in layer 2 also come from, also can flow through, sorry, okay, let me phrase it a little better. So doesn't part of the residual, information gain from the residual connection from 1 to 100, doesn't that also flow through 1 to 2 and 2 to 100 if we have a residual connections from every layer to, let's say, the last layer? Like, how do we account for that? Because I feel like that might be slightly difficult to separate, because I think, yeah, sorry.
Yes, so no, there's actually, so here's the big trick with all of this, right? You're totally, if you start to think about what that information might be, you're gonna get lost, because I cannot answer that either. You need to think about how much information it is, right? And we know what the output of a neuron is. The output of a single neuron can only be maximally 1 bit, right? If it's 50-50 chance that it fires or not fires, it's 1 bit of information. If it's less than that, it's less than 1 bit of information. So you count it as 1 bit. And then you see, okay, so in that layer, again, rule 4 says the capacity of a particular layer is restricted by the output capacity of the previous layers. Well, you could be more specific, and you could say it's restricted by its input, right? Actually, that would be a better formulation. I may actually change that. So And the point is, I don't care where the connections come from. You just count the number of connections, and they're all 1 bit, right? And so that means that as you get 1 bit of information, you can totally just say, okay, there's 14 connections going in from whatever layer, and I have 20 bits of memory equivalent capacity in the layer. That means I actually only have 14, because from whatever layer comes in, it's each 1 bit of information.
Yeah, I think I understand what you're saying, but like, let's say if the first layer have 1,000, both the first layer and the second layer both have 1,000 neurons, and they all connect to like this 1 neuron in the last layer. So, and you know, that layer also have, let's say, you know, 1,000 connections from the 99th layer. So now you have 3,000 connections going into the one of the neurons in the last layer. So does that mean the input layer, like the number of input, the maximum number of input bits is 3,000, or is it like less than that?
It's no, the input would be 3,000, but your actual layer only has 1,000 bits, right? And so your capacity will only be 1,000 for that layer.
Oh,
right.
I see.
You cannot create information, so it's the minimum of the 2.
I see. Oh, okay. I see now. Thanks a lot.
Yeah, right. Okay, no, this is why we have a Q&A session. Thanks for asking. So, yeah, any other questions like this? Okay, there are no more questions, but also we can always go back to this, and you can always ask questions A in lecture and B in office hours, by the way. So let's go to the tools that I have for you, the open source tools. So you go to github.com here. So this is basically, that is a GitHub that's public, and you have total access to that. And there's a bunch of stuff. First of all, the TF meter app, the complete source code is there. Everything you need to do to compile that thing from scratch and even modify it is in here. Okay. This is Henrik, who was with me last semester as an exchange student, and then everybody had to kind of go home during the pandemic. But he's he's also very responsive still. And so if you have any questions, just send him an email. Okay. So he also wrote a paper about this and so on. So that's basically that app that I just showed you, all the source code completely open. Okay. Now then there are 2 more directories in here. One is the capacity measurements, and one is the capacity requirement. Let's start with the capacity measurements. The capacity measurements, oops, what's going on here? Here we go. Gives you these files. And this is a very interesting one. So these were the first experiments we've done, and but they've been updated, you see, 2 years ago, where we basically went and wanted to confirm the TMK curve from McKay, you know, that the information capacity of a perceptron is 2 bits per parameter. That curve we wanted to confirm, and remember I showed you in lecture actual curves, so we tried it on Keras and we tried it on TensorFlow and scikit-learn. These curves were generated by these programs, okay? And so these are the programs. You can totally use them to also measure out your own neural networks and confirm that they're good, or actually find out that they're not good, right? So that's what it is, right? So yeah, that's basically for complete transparency. You can totally go and try out this. And for example, it would be very interesting. It's partly the project. I think it could be a project for somebody who's still looking to do that for ResNet, you know, and then confirm that the ResNet just behaves the same way, or see when it doesn't, and so on and so forth, right? And so this is basically, these are the programs that are behind the memory equivalent capacity original paper. Then, and this is much more probably what you need, is called the capacity rack Python. Okay, this is basically a program that will calculate all these numbers that you've seen, like the expected and the total memory equivalent capacity. And I also gave you all, there's the CSVs, right? So these are the CSVs for XOR and like with son of noise, completely random, not XOR, this ImageNet experiment that I showed you in lecture, and then a Gaussian, a circle, and so on. And then you can run capacity requirement on these tools, and you'll get the sort of the expected and the absolute dummy network requirement. And more importantly, you can go in and also modify the algorithm. The algorithm is exactly the pseudocode that you've seen in lecture. Okay, so I completely want you to play around with this. This is sort of the idea. This is the beginning of sort of, you know, where this all came from. Most importantly, these experiments, however, only work on balanced binary classes. There's also a warning there. If you take a look at this program, you'll see it. And yeah, so it's going to give you the max and the estimated capacity. Right? Now this program is basically again, it's very simple, and you can see like the algorithm is just this here is just the algorithm as the pseudocode was in lecture, and you can see how this kind of works. But if you now want a real tool, somebody where, I mean, this is good for understanding, right? But if you want a real tool where you actually go and take a real data set and just really measure it all out, I invite you to try the Brainome tool, okay? And the easiest way to try that out is to try the demo, and then you can go from there. So this is a web-based demo, but you should also know if you sign up and send me an email, then again, you get totally for free. You don't have to pay anything ever. You get a command line tool that will help you do real stuff. So it's available for Mac and for Linux. And then you can basically run all of these measurements from a command line or within a Python Jupyter notebook. I can also actually show you later some Jupyter notebooks on how this works. So the easiest way though right now is for you to just understand the measurements is to just take a look at this. So in the demo, you can take some preloaded data set, right? For example, you can take the Titanic data set. I don't know if you know the Titanic data set, but this is kind of a famous data set from Kaggle. And so you take the Titanic data set, it's basically a passenger list, the passenger ID, passenger class, name, sex, age, how many siblings, how many kids, the ticket number, so random string, the fare that was paid, the cabin class or cabin number, and then where they embarked and if they survived or not. And survived or not is obviously the target function. So the idea is, can you build a model that based on the passenger list and the survival yes, no, can predict which attributes, or first of all, can predict the survivability of somebody, and then also with which attributes, right? So that's the Kaggle task. And in this tool, this is basically for you trivially solved. Okay, so now we have the passenger ID and so on. And the first thing we do is not build a model. The first thing we do is measure out, is it worth building a model? So we're measuring. Now we have a result. So first of all, it tells us, yeah, so we did a test transfer, 891 instances, 11 attributes, 2 classes. The best guess accuracy, if you just say not survived, is 61.62%. Now, this comes from the fact that the class balance is basically not survived is 61.62 and survived is 38.38. Now comes the interesting part. What's the learnability? And in this demo program, what we do is we look at 2 different machine learnings. One is sort of an optimal neural network, and the other one is a decision tree. And it's always good to compare the 2. And an optimal neural network would take 118 parameters. And guess what? That algorithm is nothing else but the algorithm that you see that you have the pseudocode for. It's a little bit more elaborate these days because we do multi-class and advanced classes and so on, but the major point is that core algorithm is just what you've seen in lecture. And then we do the same for decision tree, which is a slightly different algorithm. And then, of course, there's at some point going to be algorithms for SVMs and XGBoost and whatever you can think of. And then we can say, well, okay, if we had 118 parameters in our neural network, and we know we have 891 instances, and assuming they're all correctly classified, right, then that will give a generalization of 7.55. That's purely just the number of 891 divided by 118. Okay. Congratulations. Or you go from 891 to 419, right? And then you get 2.13 in the decision tree. And that is assuming we get 100% correct, which we know, given generalization, memorization trade-off, may not be the case, but just to get sort of an expectance, we will do that. So that gives us the learnability of this data set given a machine learning. And now we ask ourselves, okay, what if we had the optimal machine learning? That's just a fictitious optimal machine learner, just like we have a fictitious, optimal encoder when we calculate entropy, right? And so in order to get there, we ask ourselves, given that fictitious optimal machine learner, we want to know if we have enough data, right? Would things improve if we added more data? And so the way we do this is we go and take 5%, 10%, 20%, 40%, 80%, and 100% of the training data, and just say, well, this fictitious optimal machine learner takes, well, 8, 9, 10, 10, 11, 11, neurons or cuts, basically, to model the data. And now that isn't a good result. Why? Because the worst result would be if it was just increasing like this. So basically going, linear with the amount of data that we add, because then we're just memorizing. The optimal result would be if this curve flattened really quickly, if it converged really quickly. And the example for this, obviously, is our 2, 4, 6, 8, 10, right? After I give you 2, 4, 6, 8, 10, you can flatten the curve because you know it's +2, and it doesn't help you to add 12, 14, 16, 18, 20, 22 anymore. So the more data we add, it stays at the same number of decision points, okay? And now that means for us in this particular case, we kind of interpret the curve automatically and say, well, the way we think about it is there may be enough data to generalize, but really we are not so sure, okay? Now, unfortunately, Titanic is the example that gives you a completely, definitely, maybe answer. We have data sets that give us, oh, absolutely, we can generalize, and we also have data sets where we absolutely know we cannot generalize. So that's what we have. So we have overfit risk, and we have neural networks and decision trees. And we have the generalization and so on. And we have always no trees, and then we calculate overfit risk. Now, overfit risk is basically saying, well, given that we know we train a network and we're probably not always optimal and so on, and we don't have a lot of instances, but we do have a lot of parameters, is there a high risk of overfitting? And given that we give more learnability, and it turns out, yeah, for neural network, there actually is 100%, you probably just overfit anyway. And for a decision tree, that's still pretty high. So what we have to do is not do any of this, but use a decision tree. So that's what we do then. So we say, let's use a decision tree, and with some effort, build a model. Let's do it, right? So now, without any hyperparameter tuning, we're building a model. In this case, a decision tree, because it seems to be the better choice, because we don't have all of this overhead associated. with neural networks. And it turns out, yeah, our best guess accuracy would have been 61.61%, but our improvement over that is 18.63% for a total of 80.24% accuracy, right? That's not so bad. And yeah, it's a binary classifier, and you get a generalization of 3 bits per bit, right? So 3 sort of equivalent of the was balanced classes, 3 instances per parameter can be predicted. And then you can actually, validate your predictor. And if you signed up, then you can also just get the predictor out and use it. Okay. We can also, just for fun, ignore all the measurements and say, let's use neural networks, and rebuild the whole thing with an actual neural network. And so that takes about 2 minutes. It predicts the time it'll take. And after those 2 minutes, we'll actually have that, and we can download that model too, and we can totally go ahead and build stuff with that. We'll see that model won't be as good because most likely this has a higher risk of both. Yeah.
Sorry. Oh, Professor, I just have a quick question. I'm not sure if you mentioned this. Maybe I just missed it completely. But like, what is the format of the data being used in this case? Is it like
a comma separated value file?
Oh, okay. So is it like a 2-dimensional? So I guess how many dimensions are there at each data point? Like, is it like a 2-dimensional point? Is it like a point in 2-dimensional space, or is it like an image?
No, it could be any. So it's basically, you could be an image. When you have an image, all you do is you take the pixels or whatever representation you have, and then you linearize it, right? It could be 1,000 dimensions, and then you have a target class. So,
I see.
For example, you could upload the CSV file that you saw the ImageNet one, which was 2 classes of ImageNet. You could take the CSV file and upload it here and just run it.
Okay, I see. So like the input could be, an image, it could be like a vector representations, or it can be anything.
As long as you fit it into a comma separated value file, right? Remember the first lecture, everything is a table, everything is a table.
I see. So, oh, sorry, go ahead. I didn't mean to interrupt.
I was just saying, everything is a table, and the table is represented by a comma separated value file, right?
Okay, I see. So I guess one more question. So, so I think if I guess the network capacity that will be required to train, classifier for specific data source. Is it like, if you have that information, can you basically just build like a compression algorithms? For example, like, you can take, I guess one can take VAE or like any generative models to basically compress the original input image, which could be pretty huge, into a representation and just learn on that representation.
Yeah.
I don't know if that, sorry, I don't know if that question makes sense, but I try my best.
The answer is just plain yes, and we have done that.
Okay.
Which is kind of nothing else but a feature extraction, right?
Right. So like, I guess my question is, can you use the information about network capacity to decide how big the representation in the VAE is?
Yeah, that absolutely is one of the advantages, because before you build a model, you saw how long this building took, 2 minutes, but compared to everything else, right, so long, and the model wasn't good. 61.61 is basically best guess, okay? Now, the more interesting part here is we measured it a priori, and we already knew neural networks have to memorize everything to do well, or because we train for generalization, we will find the most general model, but the problem is it doesn't give us good accuracy, okay? So we want to use decision tree for this as predicted, and in general, though, that's what you do. You just remeasure as you try to fiddle out with your different feature sets and representations until, and the number I would optimize for is actually this parameter count, right? Until you find the least amount of parameters in either decision tree or neural network. And also until your generalization curve here becomes really flat, right? So that it says enough data to generalize. These two I would look at, and you can play around, upload, remeasure, upload, remeasure, upload, remeasure until you find the optimum that you know. And that's only one feature. Here's the problem, right? So if you take another look at Titanic, you see there's name, there's a ticket number, a cabin. That doesn't give us anything, right? A machine learner, what would a machine learner based on 891 instances try to infer from a name? Nothing. So what you can do is you can do what's called attribute selection. You can go and click this little button, select suggested. And now you see how this unclicked? It says actually what we should use is the passenger class, the sex, male or female, and the number of siblings and the number of children, and everything else we don't need to use. So first of all, let's take that suggestion, then we remeasure it, and let's see how good it looks. You get a decision tree with one parameter. A neural network is only 49 parameters, and that seems bugged out. But in any way, point is that looks a lot better. The overfit risk is super low. The neural network still is high, but it's a lot better. Because now, if you think about it historically, yeah, it's totally makes sense. Women and children first, and of course, those that are wealthy. So the passenger class gives you an indication of your wealthiness, and then female or male is women, and then children would be the number of siblings and also the number of children, literally. So yeah, that makes total sense historically. So let's build a decision tree for that and see where we end up with.
Okay, I think this is pretty amazing, but I think I just want to ask like a quick clarifications on how the suggestion was made, because I mean you just click the button and magic just happened, but like yeah. I'm just wondering like if there are.
I'll explain the magic in a sec. So now we still get 84.92 accuracy because that is pretty much the biggest you can get, but we have a model capacity of 1 bit. What it means is the predictor is 1 if then. The predictor is a decision tree of depth 1. It means 1 if then. And that is the most general solution for Titanic that does give us the highest accuracy because we could never go over 80%. Okay, just telling you. So now how does this suggestion work, right? So I tell you how the suggestion works, right? The suggestion works by basically doing a search through all the parameters, so all the columns, right? So we create a table of only passenger ID target, only P class target, only name target, and so on. And that gives you obviously a way to measure memory equivalent capacity. And what we want to find is the set of attributes that minimizes the memory equivalent capacity, because that gives you the most general attributes, right? And so what you do is you start with 1 and you take the minimum. And then you add another 1 and see if the minimum goes down. If the minimum doesn't go down, you stop. If the minimum goes up, because then you just increase the risk of overfitting, right? So basically, that's how you search through this with calculating memory equivalent capacity. And if you do so, what then happens is you'll end up with the most general attribute, which is absolutely clear. Just finding those, you get those. So that's how powerful memory equivalent capacity is. And the funny thing is that since memory equivalent capacity obeys the triangle inequality, that search is not 2 to the power of n. That search is n choose 2.
I see. So if I have a data set that has, some attributes, they might not be, in the same category. I can also do this to select, what's the most indicative set of features that will give me a good classification result. Is that what's being implied?
No, so what you get is the most indicative set of features that gives you the most general result. And now if you say, I want to increase accuracy, right? Because, I don't know, 80 is not good enough. Well, what you do is you add some other feature manually. And you say, okay, I don't care about most general. I actually want to go to most, I want to have more accuracy because this is too general, right? And the typical thing is to, no ticket wouldn't work. Let's find something that does work. Fair actually, I think works. Yeah, so ticket just increased your neural network in your decision tree by like a factor 200. Okay, but fair increases it also by a factor 100. But I'm pretty sure if you build now, then you get higher than 80%. You get to 86 or so. And that's how you control the trade-off between generalization and memorization. Here we go. We got to 86. So at the cost of adding 86 parameters, remember the most general version was one parameter and had 80% accuracy. But at the cost of adding 86 parameters to a simplicity, making our model more complex by 86 bits, we also get 6% or almost 7% increase in accuracy, right? And that's sort of the idea here. The idea is you can play around using the measurements and then also build a model later to find the best trade-off between generalization and accuracy using the measurements, and then you build a model and then you're done. And the model, again, is built based on all these measurements, so there's no hyperparameter tuning. And we've tried this out on, as I said, and this is another link that I want to give you just for your information. So this is another GitHub Rhino/OpenML. That is the link where we can show you where we went through 176 experiments automatically without any hyperparameter tuning. These 176 were based on a capital 1 UIUC AutoML benchmark, and they're all from OpenML. And of the 176, these are both binary and multi-class problems. We beat the state of the art in accuracy in 85% of all the tasks. We beat the generalization by a factor 10 in all of the tasks, and we beat the training speed by a factor 100 in all of the tasks. That's what measurements give you, okay? And if you don't believe it, please, here's all the reproducible predictors for all these tasks. And if you want, you can just peek into one, okay? You can just go in here and see this is completely self-contained, automatically compiled using sort of the tool that I just showed you, command line tool, Python code. And this is, for example, a neural network is a 10-way classifier for some complicated tasks. Here's your confusion matrix. And by the way, here's your neural network, right? Completely transparent, pretty clear, right? This is your hidden layer. This is your output layer for 10 classes. Play around with that. It works. It's reproducible. It will give you this accuracy, right? Yeah, and then we compare that to the state of the art. You can take a look here. There's a report file. And it basically says, well, for example, most of these files are built within seconds. So you directly download the CSV from the OpenML. It takes 33 seconds, 30 seconds, 21 seconds. Our model in this case gets 100%. Well, yeah, I think these simple models are all overfitting anyway, right? If you go later on, it takes a little more, right? So now like this model here, Eucalyptus, I don't know, it takes 183 parameters to build. Okay, let's take Escherichia coli, 128 parameters, but the build time is actually longer. But you know, our model gets 92.9626%, and the state of the art is 86.31. And again, sort of 85% of those cases we win, and it's all just based on measurements, no hyperparameter. Something to look about, and then again, you can get access to this tool by basically just registering and sending an email. And the next thing to look about is what we call examples, right? So if you look at examples, you see a bunch of, for example, this is USPS measurements, and you can just open the, that doesn't work. The IPython notebook. La la la. Okay, I maybe use the PDF because I thought it's used works. Okay, and the IPython notebook tells exactly how to just basically use the tool that I showed you, the measurement tool within a Jupyter notebook, and you see like VDC measure only, how you get these USPS digits measured out, and then what you need to look at, then how to build that actual predictor, and what's the actual results, which is 92.9% for this case. It's basically all documented for you. Again, more interesting for you, for your project, to actually get these measurements out and interpret this and figure out what you want to do. That would be it for my demos. Are there any questions?
First, I have questions, but I do want to make sure other students get to ask their questions first. So I'll wait.
Okay, anybody wants questions?
Yeah, actually, I have one.
Mhm.
So I'm not sure whether it has been talked before, but maybe I'm just lost. So I'm just curious about like, what can we do if it's not a classification task?
Oh, so unsupervised, we cannot do anything. It should be a classification task. But if you have a regression task, then what you can do is you can quantize the classes, quantize the regression function into classes, right?
Yeah, so like actually in my proposal, I chose to like, the work I chose is like a image compression through neural network task. So it's also not a classification task. The error is measured by, like in the training, the error is measured by the MSE loss between the reconstructed image versus the original image. So I'm curious about, can we do anything on this kind of task?
But first of all, not necessarily with the tool here, but maybe you can. But also, you can obviously do something with the concepts that you learned in the class, right? But you know that there's a generalization memorization trade-off that has this curve, and you could start measuring out when this happens. And you can also obviously, for an autoencoder or something, the theory on how to measure the memory equivalent capacity, or how to get the memory equivalent capacity analytically, both of them completely work, right? So you can do something. It's just you cannot use this particular tool for those.
I see. Thanks.
I mean, for example, in Rishi's example, he didn't use the tool, and there's a very good reason. Because the tools didn't exist, right? These are new tools that, by the way, Rishi also built. So Rishi is actually part of this company, and he was one of the main builder of these tools.
Get it. Cool.
Any other questions? So maybe Masood, you want to go in now?
Yeah, sure. So I think we had this discussion in one of your office hours about like I guess applying this task to it's like applying this method to controls, like instead of classification tasks, and maybe we can exploit some constraints that it's present in control sequence, because only a subset of plans will make sense to execute. If like I guess given that's also dependent on the environment, but I guess do you think it will be good to leverage some like model-based reinforcement learning approaches, like predicting the next state, given like it's predicting, because I'm thinking about predicting the next state given the current state and the action, and maybe that way we like that can pose some kind of constraints on I guess the transition dynamics, so that we can do this classification task a little bit easier. Because I feel like if I can just go from raw input to the control in a supervision manner, but I feel like we're losing this sequential intrinsic structures if we go that way. But I'm not sure if that's something I should consider, or like I want to see what's your opinion on that.
So I think, let me give you my general opinion. My general opinion is this is about measuring complexity, right? The whole lecture and everything here is about measuring complexity. So complexity is a weird, interesting thing, right? The Shannon entropy itself is a weird, interesting thing. It's weird because we can calculate the Shannon entropy of any file within seconds. And then we know, given the constraints we put in, what is the smallest this file can become, right? But we don't know how to make it the smallest. In fact, there's a lot of ways that this can become the smallest in various ways. But how do I put this? We can measure how small a file can be without building a model for that file. And that is the major trick here. We can measure how small a neural network or a decision tree can be without building that network or without building that decision tree. And that gives us a way of predicting how well would this particular thing behave. And that's obviously the interesting part. And so now in your case, or for even for unsupervised or for regression, if you can use the principles you've learned in the lecture to find out a measure that can predict how well a certain algorithm would do in your control problem before you actually do the control problem, then you can choose the right algorithm. That's what this is about.
Yeah. So I think I agree with you, and I think in my task I'm interested in behavioral cloning for demonstration tasks, and I guess I want to know what size of network should I use to capture the essence of human demonstration without capturing the noise. So because people's demonstrations are very, very noisy most of the time in control tasks. So sorry.
And the interesting part in your case is if you have the map or the maze or whatever you are in, then the complexity of that maze would be the lower limit for how good a human can do, right?
Yeah.
Because
so
in the worst case, you have to still conquer the complexity of the maze. But in practice, it will be always more bits. It will be always more complex to actually solve the problem.
Right. So I think what I'm thinking about is, in the maze, if I know like the starting and the goal state, I can calculate the optimal policy, and I can tell like how many bits do I need to represent that policy. I think that should be like, I think we had this discussion in office hours, and you said that could serve as a baseline for, that's like the minimum we will need. But I think the question I want to investigate is, okay, so now that's how much you will need for the optimum policy. But since we are trying to capture something that's going to be less optimal, like how much increase does the amount of bits increased capture, some kind of properties about how suboptimal this particular demonstration is? I think that's what I was thinking about. Like, do you think that would be something that's relevant, or like I'm not, I'm
not saying it's not relevant. It's all about how you how you are able to sort of see what happens. I mean, for me, I want you to use this as a demonstration of how well you understood the concepts that are in lecture here, right? And I mean, even if you just argue that this and this and this and this doesn't fit because of X, that's okay with me, right? Before everybody hops off, because we're done soon, I wanted to go show you two more examples. One is regression to multi-class, because this question just came up, right? So regression to multi-class, there is a Python program for you, actually made by Rishi. And that program will automatically discretize your data if you have a regression problem. And if you have a problem with that program, talk to Rishi. And then there is another program that may be interesting to you, which is the speech music non. So this is a real multimedia task, okay? This is finding out from audio what's speech, what's non-speech, and what's music. And because people were asking about the comma separated value format, yeah, this is all done here. It converts sort of MFCC features from speech, which we'll talk about next time, into using different tools into a comma separated value file in the right way, such that then in the end we can build a predictor that looks like any other predictor for speech, music, non-speech, and the accuracy is quite high, 95.63%, and that's based on a bunch of samples. Okay, and that is most interestingly based just the classifier. If you use the temporal model, for example, figuring out that music isn't just there for 10 milliseconds, but will be there for a longer time, then your accuracy will probably go up to close to 100%. But we don't do temporal modeling, so you would first build the classifier. And also the classifier for an entire speech, music, non-speech task for, what is this? 442,000 samples, right? Looks like this. That's your classifier. Done. Okay. So yeah, that is the smallest classifier you probably have seen for that task. It's all because it's built out based on measurements. And in fact, how small is it? That's the measurement. Yeah, 795 parameters. Okay. So yeah, that's sort of where I want to go with this. Sort of you build this stuff and then you comment on various things based on those measurements. And please take a look at the examples and everything so to get more familiar with them. So any other questions? Okay, then my question is, who hasn't sent me an abstract yet? Who hasn't sent me a proposal yet? Let's do this. I'm going to actually stop the recording because that doesn't have to be public.